If you don't know Monte Carlo method, you are at right place. If you already know, then just sit back and enjoy. This is an amazing way to solve difficult problems by using random sampling, and it can be used in so many places from physics to finance to engineering and so much more. I will try my best to explain how it works, and if you get stuck somewhere, let me know in comments. We are going to use Python for this so that we can plot everything nicely, but all you need is just basic knowledge of Python. Okay, let's start with the first example, which is very easy to understand. You throw a ball against a wall and you want to find the coefficient of restitution, or basically how high the ball will bounce after hitting the ground. It depends on the material of the ball and the ground, and also the angle and the speed that you throw the ball with. But assume you don't know this function f of x, y, and you want to approximate it. How can you do that? Well, this is where the Monte Carlo method comes in handy. So here is our scenario. We have a floor and we are throwing the ball with some angle and speed, and we are checking if it is above the floor. And if it's not, we are recording the height. We are doing this randomly for many balls and see how it works. So we are generating random angles between 0 and pi 2 and random speeds between 0 and 1. Then we throw the ball and check if it hits the floor or not. And if it does, we record the point where it hits the floor. Now we have a list of points, and each point has x and y coordinates. The x coordinate is just the angle of the ball, and the y coordinate is the height at which it hits the floor. Now, what we want to do is approximate the integral of the function, which is the area under the curve. To do this, we use the trapezoidal rule. Basically, we calculate the width of each interval, which is the difference between two adjacent angles. Then we sum up the areas of all the trapezoids, and this gives us an approximation of the integral. The integral represents the coefficient of restitution that we want to find. Now, let's plot the points and the corresponding trapezoids. As you can see, the Monte Carlo method approximates the integral by using random samples. The accuracy of the approximation increases as the number of samples increases. We can also use other methods such as the midpoint rule or Simpson's rule to approximate the integral. These methods use different ways of dividing the area under the curve into shapes, but they all work well. Now, you might wonder why we are approximating the integral here. Well, that's because we can't solve this integral analytically. The integral of this function is not a nice closed-form expression. However, the Monte Carlo method allows us to approximate the value without finding an explicit formula. Another advantage of the Monte Carlo method is that it can handle functions with multiple dimensions. Let's consider a function of two variables. Here is its 3D plot. Now, we want to find the integral of this function over a rectangular region. We can still use the same idea of generating random samples within the region and approximating the integral using the trapezoidal rule. But now we need to generate random samples into dimensions. We can use a library called NumPy to generate random numbers in multiple dimensions. The NumPy random module provides a variety of functions for generating random numbers. For example, we can use the random function to generate random integers within a specified range. Or we can use the rand function to generate random floats between 0 and 1. In this case, we want to generate random numbers for the variables x and y. Another cool thing about this code is that we can parallelize it to run faster. Parallelization means running multiple processes or threads at the same time. In this case, we can use the multiprocessing module to run the calculation for each sample in a separate process. This can speed up the calculation significantly, especially for a large number of samples. Overall, the Monte Carlo method is a powerful technique for approximating integrals, and it can be applied to a wide range of problems in different domains. Its ability to handle high-dimensional integrals makes it particularly useful in fields like engineering and finance, where complex models often involve multiple random variables. Let's move on to the next example. This time, we are going to solve a differential equation using the Ricci equations. First, we need to define the Ricci equations. These equations relate the curvature of spacetime to the distribution of matter and energy in the universe. They are a set of nonlinear partial differential equations that are notoriously difficult to solve analytically. Analytical solutions exist for some special cases, but in general, finding exact solutions is a major challenge in general relativity and cosmology. To discretize the Ricci equations, we can use a finite difference method. This involves approximating the derivatives in the equations with finite differences. The choice of the discretization method and the numerical solver depends on the specific problem and the boundary conditions. It's important to note that the accuracy of the numerical solution depends on the step size and the tolerance of the solver. So, if you want to play around with this code, there are a few things you should know. First, you need to install the necessary libraries. You can do this by using pip install matplotlib and pi for py. Make sure that you have numpy installed as well. Then you need to copy the code and paste it into a Python file. You can then run the file from the command line by using python_file.py. When you run the code, it will generate a plot of the solution to the Riccati equations. You can adjust the parameters of the simulation to explore different solutions. Another thing to keep in mind is that the code uses a parallel computing library called MPI for PY. This library allows you to run the code on multiple processors. To use MPI for PY, you need to run the code from the command line with the N option, followed by the number of processes you want to use. For example, to run the code on 4 processors, you would type python_file.py N4. And yeah, that's it for today. I hope you learned something new, and if you have any questions, feel free to ask them down below. If you like my content, you can support me on a platform. Thank you for watching, and I'll see you next time.